Welcome back. Here is the optimization problem that we want to solve in this video. So a fence is to be built around a rectangular area. Three sides of the fence will be made with wire fencing, costing $2 per linear foot. And the fourth side will be made with wood fencing, and it would be $8 per linear foot. So we want to find the length, width, and the area of the largest rectangle that can be enclosed with $320 worth of fencing. So basically, we are given $320 only, and we have to use wire fencing on three sides, where each linear foot is $2, and the fourth side must be made with wood fencing with the cost of $8 per linear foot. The question is, what is the largest possible area that can be enclosed by the fencing? Okay, so again, at this point, you should be reading this statement a couple of times and make sure that it makes sense. So to understand more, let's draw a picture. So we are building a rectangular area, and so let's say that we have four sides. Let's say that the length is denoted by L and the width is denoted by X. Now here, it could be that X is bigger than L or L is bigger than X. So just because I'm using the word width for X doesn't mean that it is less than the length. So let's say that on this side we are going to use wire fencing. On this side we are using wire fencing, and on the right side here we are going to use the wood fencing. So the cost of this side is $2 per linear foot. The cost of this side is also $2 per linear foot, and the cost of this side is also $2 per linear foot, because that's where we are using wire fencing. On this side we are using wood fencing, so that's $8 per linear foot. So if we are building a rectangular area with width X and length L, then in this way, then what is the total cost of fencing? Well, what's the cost of this side? Well, the total length of this side is L, and the cost is $2 per linear foot. So for L we're going to get 2 times L would be the cost of 2L would be the cost of building this side. Similarly, 2L is the cost of building this side. 2 times X would be the cost of building this side with wire fencing. And the cost of this side with wood fencing would be 8 times X. So the total cost would be when we add them. So we get 4L plus 2X plus 8X, which would be 4L plus 10X. So the area of this rectangular region would be X times L, and the cost of the fencing would be denoted by C, and it is 8X plus 8x for this side, 2x for this side, 2L and 2L for these two sides. So the cost is 10x plus 4L. And so basically we need to maximize the area with the constraint that the cost must be $320, because recall that that's all the money we have to build the rectangular area here. So the question now is how do we pick X and L so that we satisfy the constraint equation and we maximize the area. So what's the maximum possible area that can be enclosed by the rectangle with sides X and L if X and L satisfies this cost condition? Well, the constraint equation, so from that we can solve for L. So L would be 320 minus 10x over 4, which is 320 over 4, that's 80, and minus 10 over 4, that's negative 2.5. So we get 80 minus 2.5x. So this is what we need to maximize the area subject to this constraint here, that L is 80 minus 2.5x. Now we can plug this in the formula for the area, and we get x times 80 minus 2.5x, which is 80x minus 2.5x squared. Now what are the possible values of x here? Well, notice that x clearly has to be positive because we are talking about the width of a rectangle. But that's all the condition that we have. Now we can also come up with an upper bound for x, I guess, if we if we say that the length L has to be positive, then 80 minus 2.5 x would be positive, in which case 80 would be bigger than 2.5x, or x would be less than 80 divided by 2.5. And then, so basically, if I require L to be positive, so this quantity would be positive. In that case, we can see that x has to be less than 32. Let me see if I can write right here. So if I make L to be positive, then we can solve this equation for x. That's going to imply that x is less than 80 over 2.5, and that's going to show us that the x is less than 32. So we can come up with an upper bound for x, but that's not really needed. So we got this, and so again, if I wanted to, I could come up with an upper bound for x by using this, by requiring L positive. So a prime of x is 80 minus 5x. Now, because the derivative here would be 80, the derivative here would be 2.5 times 2, that's 5 times x. and the derivative is 0 when x is 16. So that's the critical point, and we got only one critical point. Now let's apply the second derivative test. The second derivative of this function is -5, which would be negative at the critical point, and as a result, at the critical point we have that the area function is concave down. Since it's concave down, it has a local max at this critical point 16, and but that will be the absolute max because this is the only critical point. So then we see that the area will be maximized if we pick x to be 16. But if x is 16, then L would be 80 minus 2.5 times 16. So we have, we can use the formula for L in terms of x. That's going to give us L value 40. And then, so the length should be 40 feet, and the width should be 16 feet. And the maximum area that we can enclose is 640 square feet. So so if we have only $320, this is the maximum area that we can enclose with a rectangle, and by using the specified fencing. Okay, so this is it. That's the solution, and